So welcome, very good. Welcome everyone for this new season of the Quiver Meeting. Don't worry, Julius will still be hosting it, but he's a bit sick today, so I'm taking his place. So we are very happy to have Eran Palti today with us, and he will be telling us about scale by scale and not graph by graph, but he told me it's not against quivers. So either way.
Okay, thank you very much. Thanks a lot for the invitation to speak. It's a great honor and a pleasure. Okay. Yeah, so indeed, the title of my talk is Scale by Scale, Not Graph by Graph, Integrating Out M2 Branes. And I realized that the title maybe was not appropriate for the Quiver meeting, since nobody likes graphs more than Quiver people. But I hope that you will not take it against me. It's a quote by Polchinski, which I'll mention in a second. And it's based on this series of papers that I wrote with my PhD student, Javad Attab. Okay, so let me begin. I begin with some general introduction. I hope it's not too boring. In 1994, Polchinski wrote up his lecture notes with the title, What is String Theory? Very grand title. And then, of course, less than a year later, after writing these notes, he would discover D-branes and lead to the second superstring revolution. And what he was writing about in his notes is the following point, that if you think about the genus expansion of string theory, so we may expand the diagrams genus by genus like this, and then if we want to calculate something, we can calculate it perturbatively. So for example, we might want to calculate the free energy of strings, which is the logarithm of the partition function. And we can expand the free energy in the string coupling, and that's essentially the genus expansion. Each genus, you get a power of the string coupling squared, and that controls your expansion. And so we can write some expansion like this. But the point that Polchinski was discussing, which was known before, is that these coefficients grow very fast with genus, and they grow factorially. Well, the same is true actually in quantum field theory. Of course, if you do a quantum field theory expansion in coupling order by order, then the number of Feynman diagrams grows very fast at each order and grows factorially with the order. And so if we think about the ratio of successive terms in this series, then that ratio goes like, well, G string squared, because you get an extra factor of G string squared in this expansion. But then you also get a factor of G from this G factorial. So the ratio of successive terms at order G behaves like this. And then, of course, if you have G string, which is some finite value, then no matter how small it is, there will be some genus value which will dominate this, and then this will become order 1. And then that means the expansion will break down. Or another way to say it is that if you think of this as an infinite series, that series has 0 radius of convergence. And so what this means is that perturbation theory is only gives you an asymptotic series. That's what this is called, rather than actual function of the string coupling or of the quantum field theory coupling for that matter. This means that string theory cannot be defined perturbatively. It doesn't make sense to define it perturbatively because at some point this doesn't make sense anymore, the perturbative expansion. And it requires a non-perturbative completion. And so that means that, for example, if we're calculating the free energy, then we have this perturbative series, but then we have to add some new terms. And it's not so hard to figure out what these new terms should be like, because you can look at what is the magnitude of the smallest term in this series when this series breaks down. And that smallest term behaves like the exponential, like e to the minus 1 over gs. And so what do we know is that we expect that there is a perturbative expansion, but then it has to be supplemented by some additional terms, non-perturbative terms. You see these non-perturbative terms should come from some object whose tension goes like 1 over G string. And of course, those are nothing but the D-branes that then Polchinski discovered a few months after writing those lecture notes. And so it's natural, in fact, to ponder that this reasoning led to his discovery. And it also shows that the fact that this asymptotic expansion is not well defined is not just something academic. Well, of course, we're all academics, so it's okay to do things that are academic, but it really can teach you deep and important things about the theory. It means something important, the fact that the expansion breaks down and doesn't make sense. And then in his lecture notes, really, really nice to read, I recommend it, Polchinski noted that Wilson was struggling with the same questions 30 years earlier. This is what Polchinski said. He said, I found it enjoyable and inspiring to read about the various models he tried. He referred to clutching at straws before he found a simple and powerful answer that the theory is to be organized scale by scale rather than graph by graph. And that's the title of my talk. And of course, this was the idea that instead of defining quantum field theory through perturbation theory, you could define it through renormalization group running between fixed points, which is a kind of modern way of understanding quantum field theory properly. And then actually in his notes, Polchinski also says that, well, in string theory, we're still lacking such an organizing principle. And in some sense, the motivation for this talk is the question, can we understand string theory scale by scale, not graph by graph? So that's the motivation I wanted to. Are there any questions or comments? Or, okay. So that's the motivation introduction. So what we're going to be considering is topological string theory, because the full string theory is too hard. We're going to consider the so-called A model. And topological string theory is like a simplified version of string theory. It's a fully critical, respectable string theory, but it's simple because the world sheet theory for topological strings is taken to be a topological quantum field theory, which means that the physical quantities in the theory don't depend on the metric on the world sheet. And the target space of topological strings is a Calabi-Yau threefold. And so we're embedding the strings in the target space, which is a six-dimensional Calabi-Yau. And the free energy, by the way, this is really the full target space, just a Calabi-Yau threefold. There's no additional extra dimensions. And because they're topological, they depend on the target, they're betting on target space in a very simple way. So for example, the free energy of topological string just depends on the Kähler moduli of the Calabi-Yau. We'll call these TIs. So they give you the sizes of 2 cycles in the Calabi-Yau. And if you want to calculate something like the free energy, we can just do the genus expansion, just like we do for completely normal physical strings. This time in the topological string coupling lambda. So we can write something like this. The free energy depends on the Kähler moduli and on the topological string coupling. And so you can write this sum like so. And so we have the same structure that we have in string theory, and we can address the same questions. Again, we have this perturbative series in the topological string coupling, but then we also expect some non-perturbative corrections to come in like this, and in some sense make this asymptotic series into an actual well-defined function of the string coupling. And well, there have been many, many attempts to, and certainly partial success in trying to understand these non-perturbative terms for topological strings. So that's in some sense the first step before understanding them in full string theory. I guess one way is maybe interesting for the Quiver people is that you can do geometric transitions from Chern-Simons theories, and then localize the Chern-Simons theory partition function. And this way you can calculate this exactly. That's one way to do it. There are tools like resurgence, tools like the holomorphic anomaly you might come across, and these kind of ideas. But as yet, as far as I know, there's no. This is not yielded a general expression for these exponential terms until recently. It's the claim. Okay, so are there any questions about this setting? Because now I start going to the details of how we might try to calculate these non-perturbative terms. Okay, so that's the idea. We want to try and calculate these non-perturbative terms, but we're going to do it in a new way. The way to the approach that we're going to take to
Eran?
turn. Yes.
One question regarding the previous part is how would you pick the physical quantities that you would like to compute? Is it always going to be a free energy or
Yeah, we will just compute the free energy. I mean, that's a very general, because it's a full partition function, but I don't, yeah, that's the only thing we'll calculate here.
okay?
Okay, yeah. We're not going to calculate all correlation functions and things like this. Yeah.
Okay.
Thanks. Any more questions or?
Just one question. So here you're assuming that the Calabi-Yau is compact, smooth.
No, well, no, none of those.
None of those. Okay.
Yeah, it can be non-compact.
And
In
also,
fact, most those are the best understood settings when it's non-compact. Indeed, like, for example, this Chern-Simons geometric transitions is to a non-compact Calabi-Yau.
okay, okay, very good.
And it can be singular if you want. Yeah.
Okay, thanks.
Yeah. Yeah. Okay. So, well, I should say that. Yeah. Okay. That's it. So the way we're going to approach the problem is we're going to think about topological strings as a certain supersymmetric subsector of full type 2A strings, as the physical type 2A strings. And this was understood that this is the case in already back in 93 or so. And the way to think of it is the following. Take type 2A string theory, now the full physical type 2A string theory, compactify it on Calabi-Yau threefold. And that gives you an n equals 2 supergravity in 4 dimensions. This n equals 2 supergravity in 4 dimensions, it has the following multiplets. It has a gravitational multiplet that has the graviton in it. And then because it's n equals 2, there's a bosonic superpartner of 1 spin less. So that's going to be a gauge field. And that gauge field we call the graviphoton, because it's in the same multiplet as the graviton. And what's going to play an important role for us is the field strength of this graviphoton. So W is the graviphoton field strength. Okay. And the other type of multiplets that you get are vector multiplets. Well, there are also hypermultiplets, but we won't mention them. We're just going to look at the vector multiplet sector. That's the only thing that's relevant for us for topological strings. So the other type of multiplets are vector multiplets, and they have a gauge field and a scalar field in them, and there can be many of them. Essentially, the number of them is given by the number of 2 cycles in the Calabi-Yau, as I'll explain in a second. But the way to describe the vector multiplet sector is a little bit, the best way to do it is by introducing a certain redundancy that is then removed. So what you do is you introduce one more vector multiplet than there actually are. And you then work with these coordinates, which are ratios of these xi's. And so you see that, and these are the physical coordinates. So these are the things. So you see then Z0 is just x0 of x0. So that's just 1. So that's nothing. So that gets rid of your scalar degree of freedom in the additional vector multiplet. So there's one extra vector multiplet. So we have to get rid of its scalar and of its gauge field. So the additional scalar degrees of freedom is gotten rid of just by working with this ratio of the xi's. And these are then the physical quantities. So that's the zi's are then identified with these ti's, which are then the Kähler moduli of the Calabi-Yau. So the VI's are the 2 cycle volumes, and the BI's are the Never-Schwarz 2 form reduced on those 2 cycles. So that's the scalar sector. So that's how you give it. And then there's one more additional gauge field because we've added an extra vector multiplet. And the way that that's removed is the following. Essentially, one combination of these AIs is going to be the graviphoton. Okay, so one of them is actually going to sit in the gravitational multiplet. So that's how that gets moved. And the way to write that is to write the self-dual and anti-self-dual combination of the graviphoton field strength. So let's say W minus is this anti-self-dual combination of the field strength. And then this W minus is related to the field strength of these AIs using this relation here in terms of the xi's. So that means that one combination of these AIs is actually just a graviphoton. And then this removes for us the full additional extra vector multiplet that we've introduced. Are there any questions about this structure of n equals 2 supergravity? Okay. So Now that's the superfield content. Now how do you write the action? Well, the best way to do it for our purposes, although this is not usually what's done, in fact, it's very rarely done, but for our purposes, is to actually use superfield notation and to work in superspace. So n equals 2 superspace is something you really don't come across very often, but in our case, it will be useful. So what we do is we promote these component scalars to superfields, to vector superfields. And the same with this graviphoton field strength, we promote that to a superfield. And then the action can be written in a very nice way. It's given by an F term in n equals 2 superspace. So it's written as a d4 theta. Remember now this is n equals 2, so there's 8 supercharges. So this is an integral over half of superspace. And then there is an F term, so some holomorphic function of these chiral superfields. And this function is called the prepotential. And I put an S on it to remind us that this is the supergravity prepotential. Are there any questions about this formulation of the action?
Supergravity as opposed to what?
Well, at the bottom of the slide, we'll compare this to what's called the topological string free energy, which is also called F, but they just differ by a certain factor. Sometimes they call this the topological free energy is also sometimes called the prepotential. So, and the genus G contributions are genus G prepotentials, but there's a bit of a difference between supergravity and the topological strings, but it's not an important difference. Okay. So then what we can do is we can expand this prepotential in the graviphoton field strength superfields in powers of these guys. So we write this as sum over G like this, and this is sometimes called the genus G prepotentials. And now with the action written in this way, we can compare this to the topological string free energy expansion. So like this thing here. Okay, so
so this is already chiral, right? You only take half.
Yes.
3 components in W.
Sorry?
Three instead of 6 components in W.
In W minus.
So you're saying it's either the self-dual or anti-self-dual?
Yeah, this is this anti-self-dual part. Yeah.
Okay. Yeah.
Right, exactly. Yes. And sorry, there's no minus on this superfield thing, but it is also it's the actual super partner of the anti-self-dual part of the graviphoton field strength.
Yeah.
In fact, here what appears is the anti-self-dual Riemann curvature tensor, because this is a gravitational multiplet. So
and there is going to be a similar term with the self-dual part, right?
The self-dual part is not part of the F terms, as far as I understand. Yeah.
I see. Okay. Okay.
So, well, maybe there is. I'm not 100% sure, but we will see that we'll only be interested in the anti-self-dual contributions. So we'll only turn this guy on.
And this I is real or complex?
Which I?
On the left, the quantity which is called I. No, further left.
Oh, this is real. Yeah, this is real, but there is some superspace integration here that you should have the I here for.
Okay.
Well, I think you have to add the complex conjugate to this actually for the full action.
For it to be real. So
yeah, I need to be. Let me think. We calculate this guy. No, this guy is not. It's not real. It's holomorphic actually in the fields. So to get the physical action, well, this is holomorphic in the fields. To get the physical action, you should add the complement. But this is the same as the usual F terms in the action.
Yes. Okay.
Yeah, you should add the conjugate to it. Sorry, thank you. Yeah.
Okay.
So okay, so this is the action. This is the general way to write the action. And then we see the relation to the topological strings through the following map. The topological string free energy is identified with W squared, the graviphoton field strength, in this way, and the supergravity free potential as a function of the zi's, actually not the xi's, you have to do certain rescaling for that, is then identified with the free energy of the topological string. So remember, these zi's are just given by some 2 pi times these t's. Okay, so you just write this as a function of t and lambda, and that is a topological string free energy. So this is a kind of target space effective action way of identifying the subsector of physical type 2a strings, which are the A-model topological strings. So are there any questions about this? So that's what, so if you like, the way that you can show this, as is done in this paper, is you remember what is the effective action? It's just capturing like string scattering amplitude behavior. And so this topological string scattering amplitudes are some special part of the action, and that's precisely this map to the topological string here. Okay, so that's the target space way to get at the topological string free energy, or if you want, you can also calculate any kind of correlation function of scatter amplitudes this way as well. Are there any questions about this? This is quite important. All right. So what this means is that determining the 4-dimensional action non-perturbatively in W, the graviphoton field strength, yields a non-perturbative topological string free energy. So there is this map between the two here. And if we knew this action, not just as perturbative expansion, but non-perturbatively in the field strength, we would know the topological string free energy non-perturbatively in the string coupling. Now, perturbative, so an asymptotic series determination of the action was proposed by Guberkomer and Waffer in their seminal work. What they said was, let's integrate out states charged under the graviphoton. They will give you corrections to the effective action. And those are then identified order by order with the topological string free energy in this way. And that way you can calculate topological string free energy. And now, because the action is an F term, the only states that can contribute are BPS states. And the only BPS states in type 2a string theory charged under the graviphoton are D2, D0 bound states wrapping 2 cycles in the Calabi-Yau manifold. And so what they said is integrate out D2, D0 bound states on these 2 cycles in this Calabi-Yau. That will give you corrections to the effective action. And that way you can calculate the effective action as a function of the graviphoton field strength. And then this way you can also calculate the topological string free energy. And this is indeed a scale by scale approach, because you're actually just integrating out these states, just like Wilsonian integrating out in the path integral. So this is a scale by scale approach in that sense to topological strings, but it's still only in a perturbative asymptotic series. That's how it was understood.
But there is a question if this is the only source for the non-perturbative contributions.
Right. So at least as an asymptotic, for the non-perturbative parts, or for the
non-perturbative part, so every non-perturbative part will have a perturbative expansion around it.
Yeah.
And then the question is, so you identify a class of contributions from M2 branes.
Yeah.
So you take them into account. The question, which is not clear to me, is whether those are the only contributions.
Yeah, so
Maybe
we'll discuss that at the
others.
end, but so far I'm just talking about perturbative. Let me explain how the perturbative series is determined.
I see. Okay.
And we'll get to the non-perturbative parts in a second.
Okay.
Yeah. But of course, you can ask the same question about the perturbative contributions. Why are those is it only from integrating out these D2, D0 branes that you get these perturbative series in W? Why can't there be other terms in the action coming from some other things? And we know so far that there are no other terms. That is the full perturbative series that you get. They pick out all the terms.
And is there some physical reasoning why those will be the only ones? Some intuition?
Well, I think so, yes. I'll explain it actually in this slide a bit better.
Okay.
But I think it's even stronger than what I explained in this slide. So, but let me first of all explain the reasoning of Gruppekomma and Waffer for what they did this. So the thing is, the problem is the following. If you try to integrate that to D2, D0 state, D2, D0 states are non-perturbative objects in string theory. And that means that they're heavier than a fundamental string. So it's not clear how to even integrate them out because they're living at a scale where you're not in a quantum field theory regime, you're in the stringy regime. But what they said was the following. First of all, we should compare the topological string coupling to the string coupling. And the way to do that is to write this W squared that we had before here, not in the Einstein frame metric, but in the string frame metric. And when you do that, you get some factors of G string appearing here. And this G4 is the 4-dimensional dilaton, the 4-dimensional string coupling. It's okay. It's just the same as the 10-dimensional one for our purposes. But there's a factor of the string coupling here. And now what we see is that this is how we see, by the way, it's a genus expansion, the topological string one. You get powers of G string at each term in the expansion. But what they said was then the following. Imagine I take the string coupling to infinity. If I take the string coupling to infinity, the D2, D0 states now become lighter than the fundamental string. In fact, they become almost massless. They become the dominant contributions to the effective action. So G string goes to infinity, they are the dominant contributions to the effective action. They're the lightest modes. But then if you take G string to infinity, it looks like lambda is going to infinity, and so you don't have a perturbative topological string expansion. But this is an asymptotic series perturbative topological string. So what does it mean by that? Well, you could take a double scaling limit where you take G string to infinity and W going to 0, such that the topological string coupling is small. So you're working perturbatively in a topological string, but the D branes are the lighter states. So that's the kind of limit that Gruppekomma-Waffer calculation is done in. But G string goes to infinity means you're in the M theory regime. And so what we really need to do is not integrate out DT to 0 states, but integrate out M2 branes wrapping 2 cycles. And the D0 number is the Kaluza-Klein momentum along the M theory circle. So that's the calculation that we need to do, integrating out M2 branes with Kaluza-Klein momentum. That's the appropriate one for this limit here. And so one answer to Tammy's question is that in this limit, the lighter states in the theory are these D2, D0 states. And so you expect that they give the leading contribution to the action, or in fact, the full contribution to the action in that limit. That's one answer. Perhaps the more general answer is that essentially M theory is the UV completion of type 2A string theory, and the only BPS states that you have that wrap 2 cycles and charged under graviphoton are M2 branes. There's no other states in the theory that wrap 2 cycles that are BPS that we know of. And so that's another reason why you would expect that these are the only things that contribute. But we will see actually some quite remarkable things that towards the end of the talk, if we get a chance to, that in fact, even what we call the classical tree-level terms come from these integrating out these M2 branes. Okay, are there any questions about this so far? All right.
Yeah, I have a quick question, actually.
Yes.
So instead of starting with the type 2A, is there a way of starting it directly from M theory and realizing it as a subsector?
Yeah, I mean, the calculation is essentially an M theory calculation. It's
okay.
just that it's M theory on a circle. And so in that sense, there's always some strings involved. Yeah. But
so you can forget the type 2A completely.
Yeah, you can forget about type 2A. Yeah, just think about M theory on a circle. Yeah. Well, I'll show you exactly what the background is. Here it is. This is the calculation you have to do. Essentially, you take M theory on this background. Well, you have a Calabi-Yau, you have a circle, and then we have 4-dimensional space, which we'll take to be Euclidean, because that's where this calculation is done most easily. And the crucial point is that we want a non-vanishing string coupling. Okay, so we need a non-vanishing background for the graviphoton field strength. Mm-hmm. So we want it constant in spacetime, so we just take a constant graviphoton background. And we'll take it just along the 1-2 direction, and then also therefore along the 3-4. Is there a question about this? Oh, no. Okay, and then if you think about what are the M2 states, well, what are these M2s going to do? They're going to wrap 2 cycles in the Calabi-Yau. And so if we try to count these states or try to parameterize them, then it's going to be a wrapping number in the 2 cycles of the Calabi-Yau. That's going to be beta I, and it's going to be a genus, the genus of this curve that they're wrapping here. So these wrapping in the Calabi-Yau is given by these quantum numbers, wrapping number and genus. This is the vector because there's many 2 cycles in the Calabi-Yau. And then you're going to have some momentum running around this circle. So that's an integer n. And so these are the quantum numbers that specify the M2 branes in this background. And then we have this background field for the field strength in this R4, like this. And then we're just going to integrate them out in this computation here, in this one loop computation. So that's the computation we need to do. And then we're going to get an effective action, and then we compare that to the topological string free energy, and this way we get the topological string free energy. That's the calculation that Gubicum and Raffa did. Are there any questions about this? All right. So what will this give us? Well, one thing it will give us is, in the effective action, is a perturbative series in the graviphoton field strength, because we're going to be integrating out diagrams like this. With any number of W's. So from this graviphoton background here, we can have insertions of the graviphoton, as many as we wish. But we might get even more. And that's essentially the point of the talk. I'll talk about that. Okay, so let's look at just a little bit more detail at this 5-dimensional background, the circle times R4. So forget about the Calabi-Yau for now. We don't need, this is the metric which describes this background. And we don't need to think about it too much, except look at this term here. So this is the circle direction, dy, and here's the 4-dimensional Euclidean space. And then the point is that in this background, we have a non-vanishing graviphoton field strength. And so we need to find a solution which preserves supersymmetry with a non-vanishing graviphoton background. And such a solution was known, and the Euclidean version, the Minkowski version is in this paper here, and the Euclidean version is here in this written paper. By the way, here, this is why it's so crucial to only turn on an anti-self-dual graviphoton background. If you turn on a self-dual, anti-self-dual background for the graviphoton, it doesn't give you a back reaction on the gravity part of the equations of motion, and that's why it's actually a solution in R4. So that's quite interesting. And also it preserves all the supercharges, doesn't break any supersymmetry. That's also quite interesting. Now, the important point is if you look at this metric, there's an I here. And so we have a complex space-time metric, and that's not good. I don't know how to deal with that at all. And so what we need to do is actually take the graviphoton background, which is like this. Okay, so this is the graviphoton, so it's linear in the x's, so that the field strength is just W. We have to take it imaginary, purely imaginary. And then we're going to get a real space-time metric. And so that makes sense. So, but we pay the price that we have to work with an imaginary graviphoton background, that we'll see this is, in many ways, is perfectly fine to make sense of that. Though I won't go into that in too much detail, but it's actually okay. So therefore, if we write something like a positive quantity, like the magnitude of the graviphoton background, then we can write it as square root of minus W squared, the contraction of W. So if you see something like this, remember that W is imaginary, so this is positive in Euclidean background. So this is this is how things work. Okay, that's the 5-dimensional background when we do the calculation. And now you do the calculation. There's nothing too complicated about doing the calculation. There is some subtlety to do with this imaginary graviphoton background, and we explain it in our notes here that we released in a lot of detail how to do it. But apart from that, it's fairly straightforward to do this integrating out calculation. It's a graduate level knowledge on most parts. It was really, there's something very interesting. This calculation was really only done in detail in 2014 in this paper by Dedyshenko and Witten. It's 120 pages, a very dense paper. It's not easy to read, but they do it all the details here. So this is actually 16 years after the original Gubicum and Raffa calculation paper. In Gubicum and Raffa, they did it very quickly. But the full details of the calculation, as far as I know, were only really done here in 2014. But at least that's the only place we found it written. This is the contribution you get to the effective action when you do this calculation. And you see you get these terms in the graviphoton field strength. And these Zs are the central charges, so-called central charge of the M2 states, and we'll explain what they are in the next line for a bit. But once you have this action, remember, you can then read off the topological string free energy. So this is the contribution from a single M2 brane. So this is then what it would look like. So it's essentially, you read it off from this term here. So you see you have this e to the minus sz squared, and then this 1/sine. This is the contribution from, so this here is the loop integral essentially that you do. This is the Schwinger parameter. So you integrate over the Schwinger proper time of the M2 branes in 4 dimensions. And there's a UV cutoff, so short Schwinger proper time you cut off at some epsilon. That's the UV cutoff of the loop integral. And there's no IR cut, you integrate to the full IR. And if you do that, so that's the answer that you get. And then you can read off from this the topological free energy. This is the thing that you get. And you can see now this Zs, they depend on this beta and n of the M2 brane in this way. So you see that a single M2 brane will give you some contribution like this, which is a function of the beta, the n, and the r. That's the 3 quantum numbers that specify an M2 brane. And then you just have to sum over all the M2 branes in your theory. So you have to include this sum here. And there is a degeneracy factor, an index for each of these M2 branes. The degeneracy with respect to n is always 1, so you can ignore that. So this is just a function of beta and r. And yeah. So that's the free energy contribution that you get. Are there any questions about this?
What was the R, sorry?
The R is the genus of the curve that the M2s are wrapping.
Oh, okay.
So like sphere, torus, and higher. Yeah. Any more questions? Okay, so as I said, the first expression for this calculation was presented by Gubicum and Raffa back in '98, and this is what they wrote for it. And then this index, these multiplicities of M2 branes, are known as the Gubicum and Raffa invariants. And they are, of course, very famous. This calculation is a wonderful, wonderful, beautiful paper. And it gives you a new way to think about geometrically kind of 2 cycles in the Calabi-Yau. But the result that we find is this, and this essentially agrees with this paper of Witten from 2014, except he didn't really map it to the topological free energy, but that's quite simple. We map it this way. And the 2 expressions are different, actually, and that's essentially the main point. They're different in a very subtle way, though. So, for example, you see the difference is that you have a z bar here and no z bar, and here is z mod z squared and no mod z. But if you rescale s goes to s over z bar here, then this z bar goes away and this mod z squared goes to z. So, and ds over s is invariant. So rescaling s goes to s over z bar makes this integrand into this one. And then there's no problem here because epsilon is going to 0, infinity is infinity. So it seems like it's not too much of an issue, but yeah. So it looks like they're the same thing, but they're not the same in the following sense. If you rescale s to s over z bar, then first of all, that's a complex rescaling. So this integration range would actually be over, instead of the real line, some straight line along the complex plane. But that's okay. That doesn't really change much. But the important point is that this rescaling depends on the n for us. So if it was just one contribution with n, then fine, these 2 things would be basically the same. But if you do a sum of the n's, then once you do the rescaling to this, now there's going to be some issue here with the fact that the coordinate, the integration line is going to be different for each n. So that's what we'll see that in a bit. So that's essentially the historical situation, and that's why we wrote our paper saying that this is really the result that we find, and we'll see that this gives you something much more than the Gubicum of Raffa one. Are there any questions about this? Or,
So sorry, I don't understand the difference. And if you evaluate, so each of the integrals n by n are equal, right, in the top line and in the bottom line.
Yeah.
So the result is the same. Like what's
I will go. Maybe you ask me again in like.
Yeah, maybe I'll wait. And
I will explain very clearly the difference between them in the next 3 or 4 slides, because that's one of the issues in the paper. Okay, so let me just go ahead and come back to your question, if that's okay, in like 5 minutes. So let's take the Guber-Kommer-Waffe expression first, and what we want to do is manipulate it. Essentially, we want to bring the sum over n inside the integral, and that's what Guber-Kommer-Waffe did. And you can do that, well, since this integrand is the same here, you just bring it inside the integral, and then you see, because the z has a 2 pi I n in it, you get this sum over e to the 2 pi I n s. And then you can do Poisson resummation, exchanging this for some of the delta functions. And then the delta functions make this integral trivial, so you just get this expression here. So this is the sum over n. So now there's no sum over n here, instead of the sum over these k's of the delta functions. And this is usually how the Guber-Kommer-Waffe expression is written. And it's important that this is really an asymptotic series. You expand this order by order in lambda. So for example, if you want to get the genus 0 Guber-Kommer-Waffe, the genus 0 pre-potential is Guber-Kommer-Waffe, you expand this leading order in lambda. And so you get this expression here in terms of genus 0 Guber-Kommer-Waffe invariant, and you can do it at higher and higher genus. But this is really we think of this as expanding in lambda. However, since you can only expand this sign when k times lambda is small, but k is being summed to infinity, this only makes sense at lambda going to 0. So that's why this is really an asymptotic series. This is the Guber-Kommer-Waffe asymptotic series. Sorry, I just don't know my time, how am I doing for time, but okay. Yeah, and then again, there are many attempts to try and complete this asymptotic series to something that's actually a well-defined function for finite values of lambda. All right, so that's the Guber-Kommer-Waffe calculation. Are there any questions about it? Or, okay. Now, if we go back to our result, we're going to evaluate it, and we'll see why it's different. And to do it, we're going to look at the simplest setting possible, which is when the important thing will be the sum over n. So the sum over beta and r is not going to be important for us. So we're going to look at a situation where all the invariants are 0 for beta r, apart from just alpha 0, 1, which is 1. So that means all we have is just a single M2 brane wrapping genus 0, well, NS2, just in the Calabi-Yau. In fact, that's the case for the so-called resolved conifold. Okay, so we're just going to do this simple example. So then the free energy looks like this. If we're going to do a change of variable, we're going to send un to s times z bar n. So then we make it look more like the Guber-Kommer-Waffe expression. So now the integrand looks like this. So that's a bit like dividing by over z bar. And then we have to remember that now we have the integration, because this is complex. We're doing an integration in the complex plane of u. And it's going from 0 to some straight line at some angle theta n, which is the argument of z bar. Is that clear? So s was going from 0 to infinity, but now we've rotated it by a complex number. So now we're doing integration over some line in the complex plane at an angle like this, where this is the angle, the argument of z bar. And because inside the integral u is just a dummy variable, we can call all the un's the same u. But we have to remember that this transformation depends on the n. But we see that because we keep track of the line that we're integrating over. So is there any questions about this? Because this is sometimes the important thing. So we have a sum over n's, and we have the sum over these integration lines in the planes along here and along here, infinite number of them. But each integral is over a different line. That's the important point. As opposed to the Guber-Kommer-Waffe one where they're all in the same line, they're all on the real axis. Now, you have all these integrations over the different lines, and but of course, because this is a complex plane, we can deform the integration lines. But we can do so as long as we don't cross any poles. So we should look at the poles of this function. This is a meromorphic function, so the important things are the poles. And then we see that there are poles when u is equal to 2 pi an integer multiple of 2 pi over lambda. Then we get the zeros here in this sine function. So there are poles all along this real line at integer values of 2 pi over lambda. So that's the picture that we have. Are there any questions about this picture? Okay, so what this means, though, is that we cannot deform these lines in the top quadrant to coincide with the lines in the bottom quadrant, because then it would cross these poles. So the best we can do is bring all the lines in the top quadrant on top of each other to one line here along some angle theta plus, and then all the lines in the bottom quadrant to the same line along with some angle theta minus. And that's it. That's the best we can do in terms of deforming things without crossing any poles. And then we can bring the sum inside the integral, but we have to do two sums. One sum over here and one sum over here. Okay, so we have this integral here, theta plus. So we have all the kind of positive ends, if you like, that we can bring inside because they're all in the same line now. And then we have another one, which all the negative ends. And then when you do the summation, it's not so hard to do it. You just get a geometric series. So you get like a 1 over 1 minus x here. So you get the 1, this is what you get from the summation, and then this is what we had before. But you get two contributions, one along this line and one along this line, and there's a minus sign between them. And we've introduced this NB, which is the following integer. It's the biggest integer that's inside b over 2 pi, like this. So this is what you get now when you bring the sum inside. Because we have a minus here, we're essentially integrated from infinity to 0, then from 0 to infinity. And then you can show that the contribution at infinity vanishes because you have this e to minus tu, so it's exponentially vanishing at large u. And so you can actually complete these two integration lines into a contour integral, like this, over this contour here, which the contour goes over all the real axis, apart from the 0, which we've excluded. And so what we find is that when you sum over the ends, you get this result here as a contour integral. And if you want, you can then reinstate back the sum over the betas and r's, because this is a result for just a single M2 brane, and you get this integration. So this is the result that we find for the free energy, as opposed to the Guber-Kummer-Waffe one. And we propose that, in fact, this thing is not only the perturbative asymptotic series, but in fact is the non-perturbative free energy. It's actually the so-called holomorphic one, which we can discuss maybe later. And the reason that we propose that is that let's look at this contour integral. So we have a contour integral like this. It's including the real axis on it. And so it's just going to localize to the poles of the integrand. Okay, so it's a contour integral of a meromorphic function. And let's look at the poles of this integrand. Well, we have poles at any positive integer values of u, because then e to the 2 pi iu is 1. So this is a pole here. So this is going to give us a bunch of terms evaluated at u being an integer. So they're going to look like e to the minus beta t times some integer. Those are precisely the not the exponential terms in the Guber-Kummer-Waffe calculation that we find, these exponential terms here. So it's going to reproduce all these terms here. You see that's an integer times beta times t. Those come from these poles here, an integer times beta times t, all the positive integers. But we also have poles from this guys here, and they're going to be at 2 pi times an integer over lambda. So then when we evaluate them at that pole, we're going to get something like beta t times 2 pi over lambda. But that's like e to t over lambda. That's a non-perturbative contribution. So these poles are going to give us the non-perturbative contributions to the free energy. And that's the new thing. That's the new thing that we find. Yeah, so that's the important point. Are there any questions about this? Let me just check the time. Okay, I've nearly run out of time. That's a shame. Okay.
Yeah, don't worry too much about time.
Okay. Are there any questions about this result? That's essentially the main result, though. Yeah.
So depending on whether lambda is large or small, like compared to 2 pi, I guess the poles Like in a way, you exchange the perturbative and non-perturbative contribution.
Yes, exactly. I will talk about that, in fact, later.
And the reason for the mismatch with the other formula is because it's this exchange, right, of the sum of the integral, which was illegal.
Right.
That's why you lose the non-perturbative terms.
Yeah, it all actually, though it looks like a very small difference between this and this. Everything is in the difference between these two formulas.
But these are, so you agree that these two lines, they are still perfectly equal, but it's then when you proceed to exchange the sum and the integral in the top line, because it seems that you are allowed to.
This. I mean, the integrands are equal, but the sum here, these two expressions are not equal. I mean, this includes non-perturbative contribution. This is just perturbative series.
It seemed to me that
there's a sum.
Yeah. But then in the next slide, you exchange the sum and the integral in the first line. And it seems to me that that's where here, when you go there, now it's no longer equal. Is that?
Yeah, but it's also not equal. I mean, you just, the fact that this is perfectly fine mathematically, you can do it. So this tells you that the first line is just this. This is this. On the other hand, this is
not, I understand.
It's not it's this.
This I
and
understand.
in fact, you can also do this contour integral if you want, and you can write it like this. So you see, you get these are the Guper-Komma-Waffe terms. You reproduce the Guper-Komma-Waffe series, but then you get also terms that go like 1 over lambda. We define this lambda bar, which is 2 pi. And you can just calculate the whole thing very explicitly. And you get, these are non-perturbative contributions. Yeah. Okay. Are there any questions about this calculation? And the claim is, the proposal that we have is that this is in fact the full thing. This is the full free energy for topological strings. We'll talk about whether that's true or not a bit later, but yeah. All right, so that's the idea. And this is in some sense scale by scale, not graph by graph, because what we did was just integrate out M2 branes, and we didn't get a perturbative graph expansion anymore. We didn't get an asymptotic series, but we got a full non-perturbative function. That's the idea of the talk in the quote. All right, so yeah, so the first thing you do if somebody gave you the exact non-perturbative partition function of string theory, at least topological string theories, you might ask, well, then if it's exact, what does it behave like at strong coupling? And indeed, you can, this thing behaves quite nicely if you invert. So you could do an expansion in 1 over lambda, like this, in this H bar. And then you should do this change of variable to mu. And this was known already from non-compact cases, which are due to Chern-Simons theories that you can then do localization and that kind of stuff with. But we just do the same variable here for this. This is completely general what we wrote. It's true for any Calabi-Yau, non-compact, compact, doesn't make a difference. It's just an integrating out calculation. When you do this change of variable, you essentially exchange the perturbative and non-perturbative poles, as you mentioned. So now these things give you things that go like U over H bar. So this gives you non-perturbative in H bar, and this gives you perturbative in H bar. So it's a little bit like a kind of S duality that you have. But it's a little bit subtle, it's a little bit twisted in the following sense, that if you now calculate the free energy as an expansion in H bar, so it's an expansion about strong coupling, about infinite coupling. Let's call them the lead. So at recoupling, you have F0 as a leading term. Here you have this J0 as a leading term. And then the relation between J0 and F0 is such that J0 is actually the period. So it's not quite F0, but you have to take this combination of the F0s. So it's a kind of S duality in the sense that you go to strong coupling, you come back to yourself, but you don't quite come back to yourself. You don't go to F0, but you get the period instead. And that's a very important thing, actually. Yeah. Are there any questions about this? This is what the strong infinite coupling expansion for topological strings we propose looks like. Yeah. Okay, and of course, you can also evaluate it order 1. So this is really the exact thing. So you just evaluate whatever you want. So the other interesting point to evaluate is the self-dual point. When lambda equals H bar equals 2 pi, that's the self-dual point. And then you find actually something quite interesting. You find that the expression simplifies really considerably, and you only get, for example, contributions from genus 0 and genus 1 terms. All the other higher genus things vanish, and you get a really simple expression here. This simplification, we don't know what it means in general, but in the case of the blown-up conifold, which is a certain non-compact setting that's dual to ABJM theory on the three-sphere by geometric transition, then this special point is the point where the ABJM theory enhances to n equals 8 supersymmetry. There's 2 points like that. So this, I would guess, is some kind of general enhancement that you get a self-dual point in topological string theory or in string theory. We don't know exactly what this means, because this is true for any Calabi-Yau, also compact ones. So yeah, any questions about this? Okay, I just have a couple more slides. Yeah, so actually, when I wrote this free energy, I write this exp here, because what you get from these calculations are always just the kind of exponential contributions to the p potential, and that's what usually people call free energy in the sense of topological string calculations. But in fact, this also has some polynomial terms. F0 and F1 have polynomial contributions in the t's. And usually they're not, we don't know how to get them from integrating out. They're just put in by hand, essentially. But there's something quite interesting now. If you look at the resolved conifold case, which is just a single M2 brane, then we have this contour which doesn't include the zero pole, but goes as close to it, infinitesimally close to it, goes to infinity. But now if you extend the contour to include the zero pole, so that means that you complete the Schwinger integration to the infinite UV. Because remember, U is just S times Z bar, and S is the Schwinger proper time. So S equals 0 means you do a loop at 0 Schwinger proper time. That means it's infinite momentum. So that's the infinite UV. So you can UV complete the integrating out by including the zero pole. And when you do that in a resolved conifold, you get the contribution from the zero pole in this thing. And that precisely gives you a polynomial, and exactly the polynomials that we expect for the resolved conifold, which you can calculate by geometric transition from Chern-Simons theory. And this is very interesting. In fact, this is the whole reason why we got into this business in the first place, because these polynomial terms are the leading classical supergravity terms in the action. These are not corrections to the classical leading terms. These are the leading tree-level kinetic terms in the action. If you put this T cubed in, so you promote it to a superfield, do the integration of a superspace, you get the tree-level two-derivative kinetic terms in the action, the leading ones. And so now we reproduce the tree-level action from integrating out M2 branes. So this is really an example of what you would call emergence, that the tree-level dynamics of these fields are emergent from integrating out M2 branes at one loop. So that's a very interesting thing. Now this works, this extension to the zero, just extending the contour over zero, works for the resolved conifold. For more general settings like compact Calabi-Yau, you have to do something more subtle, because you cannot just extend it. You have to go to the period representation and then extend that over the zero. And you can do that, but I won't go into those details. And then I just want one last comment. There is also an Neguri-Waffer formula, which is like the open string version of the Guppy-Waffer formula. In that case, you do a partial integration of n equals 1 superspace only, because what they do is they, instead of taking D2 branes, you take D4 branes, and the D2 branes acting on D4 branes, and the D4 branes are just filling R2 subspace of R4. So then you have an integral over R2 subspace, which is just half the superspace. This is an n equals 1 F term. And from the M theory perspective, this is integrating out M2 branes ending on M5 branes. Again, this is the answer that they give, but the same thing as what happened goes through here, and this should really be written, we propose, as a contour integral, and this then captures now non-perturbative contributions to the open string sector in string theory, essentially coming from integrating out M2 branes ending on M5 branes. Okay, so to summarize, we revisited the calculation of Guppy-Waffer Waffer of integrating out M2 branes and Calabi-Yau manifolds to yield a topological string free energy. We find a different result, and one which yields the non-perturbative terms in free energy. The new expression manifests qualitatively new physics, such as dualities, enhancement points, emergent dynamics. And we believe that it's the full exact holomorphic expression for the free energy. I'll talk about what that means in a second. And of course, there are numerous potential applications. We've only just begun to explore this formula. For example, you can use it to calculate exact black hole entropy according to the OSV conjecture. You can study this emergent dynamic story more. Yeah, so the big open question, which is also the one Ami already asked, is could there be other missed non-perturbative contributions? So certainly there are other non-holomorphic terms, and these correspond to non-local terms in the effective action, which comes from integrating out massless modes in the integrating out interpretation. So we only calculate the Wilsonian local effective action. And these non-local terms in the action correspond to non-holomorphic terms in the free energy, and they are controlled by what's called the holomorphic anomaly equation. But if you know the holomorphic one, then you also know these non-holomorphic ones using this holomorphic anomaly equation. So we don't capture these non-local terms in the effective action, but they are not so hard to determine once you know the holomorphic ones. At least we think so. I haven't gone into the details of it. We integrate our M2 branes. The nice thing is that the integrating out of the M2 branes is an exact calculation. So we don't expect any more contributions from this M2 calculation. It's exact because it's an F term, and there's certain scaling arguments which tell you that even if you include corrections to the M2 effective action, it will not give you contributions to the F terms. There could be M5 contributions maybe that we're missing, but usually one does not integrate out solitonic states. So if you like, M5 branes and M2 branes are not mutually local from the four-dimensional perspectives, and normally you just integrate out the fundamental states, which is the M2. There could be some contributions, but I would say that if there are any contributions from M5 branes, they would give you, again, non-local terms in the effective action. So they will not modify the local result of the effective action, which is what we then match with a holomorphic thing. So I think this is a question. I think there are no contributions. I'm not sure. Unlike here where we know there are some, but I'm not sure. But if there are, they would give you non-local contributions. Maybe we're missing some dynamics for multiply wrapped M2 branes for the high wrapping number, because wrapping M2 branes multiple times is not so well understood. But in this paper by Witt and that, they give arguments that we are not. It doesn't look like we're missing anything here. Yeah, so it's not clear to us what else could contribute to it. So that's why we think that it's probably the exact expression. Also, it passes these non-trivial checks, like this S-duality behavior and the self-dual points implication. None of those would be true if you added some more non-perturbative terms, because they really rely on a full non-perturbative contribution. So it looks and behaves like the full answer. It has no problems at any value of the string coupling. It gives you finite answers and perfectly nice. And so it's not clear to us that anything else could ever contribute to it, but it's still, as I say, early days of exploration of this formula and approach. Thank you. Yeah. That's it. Yeah. Oh, okay. 5 minutes, not so bad.
Okay,
Yeah.
Thank you very much. Thank you very much for the talk. We had a few questions, but if there are more, we can.
Yeah.
Yes, go ahead.
Thanks for the nice talk. Can you show you had this slide with the lambda equal 1, the self-dual point?
Yeah.
Yeah. I wonder if there is a connection to, there is that non-perturbative topological string proposal in terms of the S5 partial function of Waffa and Lockerts.
In terms of the what, sorry?
Of the S5 partial function. So if they have at least local Calabi-Yau threefold, you can think of it as, well, there is this correspondence with of topological strings with Nekrasov partial function, and then Waffa and Lockerts had proposed this like gluing of 3 partition function of Nekrasov, which are essentially, which is like an S5 partition function.
Like this topological vertex. Is this what you mean?
No, it was what they called a non-perturbative proposal for the topological strings as well. Well, because it looks similar to that, because I know that in some limit, like certainly for all these local Calabi-Yaus, it will look like precisely this when you have this trilog which looks like the prepotential for just the you know the Sylvester-Wheaton prepotential for the 5D theory that you would get on the same Calabi-Yau. And then you construct holomorphic things like that by having the trilog minus the dilogs and so on, exactly like this.
Yeah, I'm not sure, but perhaps I'll make a comment that this expression here, this a lot of this is captured by the non-perturbative expression for the resolved conical was known by this Nekrasov-Chatrili limit. There's other ways to do it as well. But there are some things that this captures more than that, to do with things like, for example, I mean, when lambda is rational or integer or something like this. So for non-compact cases, like I say, for example, for the blown up conifold, this is also known. And in fact, we know what this means, the special enhancement points. The non-compact cases that you discussed, I'm not sure about the details of them, but I would not be surprised if this is known for some non-compact cases examples, usually just by duality with Chen-Simons theories. But the important thing is that this is true for any Calabi-Yau.
Right.
Non-compact, but also compact, and any toric thing, because this is just a group of Kummer-Waffe calculation. So just as in Kummer-Waffe is true for any Calabi-Yau, this is true for any Calabi-Yau. That's the important thing, I think. Yeah. So the fact that it happens for every Calabi-Yau is in some sense the new thing. The fact that this simplification was known to happen for certain cases was already known. Yeah, that's all I have to say. I cannot.
Oh, no, absolutely, it's pretty amazing. I have a naive questions about when you say it's a non-perturbative thing. That is it clear that it's when you even in Kummer-Waffe when we have the various sums over when you have the sum over in particular all the curves, is that clear that that's converge and that
yeah, so that's a good question. Yeah, that's a very good question. So indeed, like here, for example, it could be that if you bring this inside the integral, you'll get new poles or something like that. It might not be convergent in this sense. So this we don't have. We thought about it. We think the answer is no. We think this is there's no new contributions from this sum of. So we think that this converges. But it's very hard to show it because we don't have closed expression for it. But there is one part which we know is convergent, the genus 0 part, which is still an infinite series. And the reason is that we can go to this strong coupling, and then you have this S duality, and it's mapped to the period. And the period, we just have we know is perfectly fine. Well, we think it's not. This map is actually a little bit non-trivial, but yeah. I mean,
so in Gen 0, it's the mirror. You can use mirror symmetry and.
Yeah, exactly. So that's essentially why. But for the high, we're not sure. But in some sense, the interesting thing that we find, if our expression is true, is that the non-perturbative contributions only come from genus 0, because they're associated to these poles here. So that's this pole. Okay, it's a strongly coupled, but there's also the weakly coupled one. You only get a pole for r equals 0. So you see that when you actually evaluate this integral, you get just the Kummer-Waffe result for r being 1 or higher. So that there's nothing new here. And then only the genus 0 part is where the non-perturbative contributions come from. So I'm not sure if some people might think that that's a bit strange, right? I don't know, but that's the result that we get. So in that sense, we think that this sum over the genus part is quite well behaved because it essentially gives you the period. But we cannot prove that this is convergent in generality because we don't have a closed form for the Kummer-Waffe invariance in generality. And then this convergence, okay, that's something else I don't know, but that's the same as the old story. But yeah, we don't think there's any non-perturbative contributions from these higher genus things. By the way, that's another open question. Why only the genus 0 gives you non-perturbative contributions? We don't know.
So if I think back in terms of string theory and in terms of, so are those non-perturbative contribution like branes, or what is the interpretation in type 2A?
Yeah, so that's another good question. We think that they are sort of branes, but of course, since this is a 2-cycle, Type 2A doesn't have instantonic branes to wrap 2 cycles.
Mm.
But the thing is that the topological string coupling is not just string coupling, it's also the graviphoton field strength, which is like a derivative expansion. So the topological string coupling is a little bit like a mixture of S-duality and T-duality. That's why you always get this mirror symmetry coming in. That's why we're finding that when we go to strong coupling, we get essentially the mirror curve, the mirror D6 period. And so it's somehow a bit like D1 branes in the A model, wrapping 2 cycles. So if you think, better way to think about it is a D3 branes in the mirror setting, and I think that's better, maybe a better way to think about it. So we think that that's a D-brane interpretation of it, but we're not. This is something. These are all things to be explored. We're not really 100% sure. Yeah, there is actually a nice. I've not had a chance to mention it, but there's a nice physical understanding of these non-perturbative terms, which is also true in QED actually, and we describe this in my notes, that if you integrate out the electron in QED, you get an expansion in the photon field strength. Disintegrating out the electron in QED is called the Euler-Heisenberg-Lagrangian, and it was done by Euler and Heisenberg in 1936. And that Lagrangian actually has non-perturbative terms in them. And so if you integrate that electron, you actually get non-perturbative contributions to Lagrangian. And those non-perturbative terms are basically the Schwinger effect, where the electric field decays to electron-positron pairs. And so our non-perturbative terms are basically the same story there. If you integrate that the electron, you actually get Schwinger effect physics. And so this is something similar here. Of course, it's a supersymmetric setting, so you don't get any time variation with the decays, but it's a little bit like that. So yeah. Again, like I said, it's early days. We don't know what a lot of this stuff means. We just did the calculation. So yeah.
Thanks. Sorry, I have to run. Thanks for the nice talk.
Okay, thank you.
So I was wondering, maybe it's a vague question, but since you talk about interpreting the perturbative and non-perturbative contributions in other frames, so if you dualize everything until you reach the brane webs, so you don't have any more the singular Calabi-Yau, but you have now some 5 brane webs. Do you know if there is an interpretation of, I guess it's a general question, of the non-perturbative terms there? What do the M2 branes become?
You mean in a non-compact setting?
Yeah, non-compact, yeah. Non-compact singular. Like for instance, the conifold, if you do all of this, then you would just have 2 intersecting 5 branes and
Right. Yeah, it's a little bit, there's some subtlety to do with this brane dual, because the geometric transition occurs at basically 0 volume. That's when you can map the partition function of the topological strings on the Calabi-Yau to the partition function of the geometric dual gauge theory, which is some brane wrapping some 3 cycle or something like that. Now, what can happen, and we haven't really published it, we've looked at it though, is what can happen is at that point, some of these non-perturbative contributions can disappear at that 0 volume point. And then, in that sense, you would not see them in the dual Chern-Simons theory. And in fact, this happens for like in this Guri-Rafa calculation. You can show that yeah, but of course this geometric transition is always done by some analytic continuation. So you go to 0 volume, then you map the partition function of the dual gauge theory, like the brane theory, Chern-Simons theory, and then to the topological string, and then you analytically continue. But this analytic continuation can sometimes miss these non-perturbative. I mean, because if you're sitting at a thing where there's just no term there, and you do analytic continue, you can miss it. So that's the subtlety that. So I'm not 100% sure if they are even present in the dual.
Yeah. Another way of saying this is maybe you cannot analytically continue because the function is just not analytic, right?
Well, I don't know if it's not. It's just would just be what we're finding is that sometimes these would just be 0. So it's just normally what you get is some function. The way you do geometric transition is you go to 0 volume and then you get some function of just the B field, and then you analytically continue that, or you complete it to the Kähler complex field, and you go to large volume or something like this. But if there's no term there at all, even without a B field, then you just don't see it. So that could happen, but I'm not sure this is completely open thing, but we're just seeing that in certain cases. So I'm not even sure if these non-perturbative effects can be seen in the dual Chern-Simons theory or not.
Okay. Okay, thank you. Are there any other questions? If not, let's thank Eran again.
Okay, thank you very much for the invitation.
Thank you. And I will stop the recording. Recording.